Sorry.
Welcome everybody to the morning session of the second day of our conference here in Almaty. The first speaker today is Jaroslav Dittrich from the Nuclear Physics Institute of the Czech Academy of Sciences in Prague. Please, Jaroslav.
So thank you for the opportunity to speak at this conference. I'm going to speak on the Dirac particle in a one-dimensional box with moving walls. It's a common work with Saparba Yakmanov and Davion Matrasulov from Tashkent. In fact, published in physics letters.
Okay.
Huh?
Middle one.
Yeah. Excuse me, can I? Huh? Okay. Okay, sir, thank you. So the motivation of this work is one dimension of motion of electrons in some solid nanostructures or in some narrow graphene nanoribbons, where the electrons are effectively described by Dirac equation, at least in some cases. In such structures, a confining walls can be formed by laser beams, forming so-called optical traps. And if these walls are moving, we can have just a possibility of somehow tune this system on to drive the electrons. And this is a motivation. Here is just a idealized scheme of such systems. There is the graphene strip on which a laser is switching, and this laser beam forms this wall. If it's moved, we have an interval with moving wall. Schrödinger equations with moving walls was studied already in 90s and even before. For example, known papers are of Makovsky and Yazavi. And next slide. Okay, they transform it, this equation to fix the interval. Some conditions on the small motion was find under which separation of variables possible and exact solutions are found. So later, Dodonov studied the Casimir effect in such problems, and Piershogin and Pronin in fact, modified the time derivative in these equations studied by phase. Sheba was studying Fermi acceleration, showing essentially that for smooth moving of the walls, there are no Fermi acceleration in the non-relativistic quantum systems. Further, the problems similar was studied recently by Rachmanov, Tiang, Matriasulov. They at external potential study Fermi acceleration and quantum force. Further, Rachmanov, Tiang, Matriasulov, and Noyel were studied a PT symmetric version, which they achieved by putting Robin type boundary conditions at the ends. However, Robin condition with imaginary constant. And in fact, we have learned much on this by the yesterday talk of Sapphire Boy. Dirac equation was studied by Sobolev, Matkasov, and others, for example, in 2009. And let us move to our model. We study the Dirac equation of this form on a moving interval. In fact, it's one-dimensional case. So we have one space, one-time variable, and our spinor has two components. In this 1+1 dimension, in fact, there is only one set of Dirac equations, of Dirac matrices. All such sets are connected by similarity transformations, so it's fully irrelevant which we take. We take just this. As boundary condition, we took the Dirichlet boundary condition for the upper component of this spinor. And this is just one possibility how to achieve the self-adjointness of this Hamiltonian. In fact, there is a one parametric family of such self-adjoint Hamiltonians, and we took just one as an example. If we consider probability of the finding particle in this interval, it is not conserved. So this is the reason why this Dirac equation is not physically suitable for such case, and we next slide, please. And in fact, the reason for this is such: if current is zero at the endpoint, which is more or less a condition for the self-adjointness of the Hamiltonian, it means that particles are in a sense standing there. However, if the density isn't zero at this endpoint, the moving wall is, say, moving through them. So this is an interpretation of the fact that the probability is not conserved. So we should consider, to avoid this, also drift of the particles by the support. And this, in fact, it can be described by just by this same dilatation operator. The same non-probability conservation occurs for the Schrödinger equation with Neumann boundary condition. And it was noticed by Piechurkin and Bronin in 91. And they proposed to introduce the modified time derivative, which takes into account this moving of the support. So we obtain such kind of time derivative. Here. Here you see with direction of time, in fact, is a well-known generator of dilatations. Okay, you can also interpret this time derivative as a kind of variant derivative in some fiber bundle, but it's not so important for us. Okay. So we pass to a modified Dirac equation where the time derivative is replaced by this, say, covariant derivative, and okay, and we shall study this equation. In fact, if you look at this covariant derivative, you also might see that it is similar as time derivative in the equations of hydrodynamics. Now probability is conserved, and we shall study this equation. We transform our problem to the fixed space interval. So we just scale this space coordinate, and we also choose a new kind of time variable. And as a result, we obtain again Dirac-like equation, but now the interval is fixed, but there is a term which looks like time-dependent mass. Analytic solutions of this equation can be found for zero mass or for linear movement of the wall. In general case, we wasn't able to obtain analytic solutions, so we must choose a stable basis, expand, say, functions into it, and then solve this numerically. As a basis, we choose eigenfunctions of the zero mass Dirac equation of the well-known form. Expansion is here, and tau are some coefficients. Putting it into our equation, we obtain equations for these coefficients an. And in fact, this separate equation for coefficients A0, which can be just trivially solved. And then we have equations for other coefficients. And in fact, it separates into pair of equations for these coefficients an and a minus 1. with here this simple equation. It's clear that the unique solution of this equations exist for initial values given, and in fact the evolution of this coefficients of this pairs of coefficients is unitary. Of course, it's immediately seen from this equation. Now let us consider average kinetic energy to study, say, so-called Fermi acceleration. So we compute mean energy. It's also separates to parts with different n, where the first is just trivial and it's constant, and other terms are of this form. You see here some quadratic form of these coefficients, a n and minus n. And it's clear from the unitary evolution of these coefficients before that this energy remains bounded. Of course, for the length of the interval bounded from below uniformly. So there is no unlimited Fermi acceleration in this model. Here are the pictures of numerically computed evolution of kinetic energy. These calculations and pictures were prepared by Saparboy Yakmanov. And you see what you expect that for expanding coefficients, expanding interval, the energy is decreasing, while for contracted interval is increasing. Of course, this contraction is possible also only until we reach the zero length of the interval. Here are time evolution of the energy for oscillating wall. Okay, for several parameters, and you see again that the evolution of the energy is oscillating. We consider also so-called trembling motion of Zitterbewegung, which was discovered by Schrödinger in 30s. However, and they result in some interplay of the positive and negative energy states. In fact, in the elementary particle physics, now this Zitterbewegung is considered mostly by most people as an artifact of improper quantized Dirac equation, which disappeared if you can under properly second quantized equation. But if we use Dirac equation as an effective equation in solid states, it is expected to be as a real effect. So again, we compute the mean position of the electron. It's again some quadratic form here, infinite quadratic form of these coefficients. And also we consider the quantum force, which means a force on this wall on the electron, vice versa. Of course, it's given by this energy as the work or energy is force times times pass. Calculated it again in the terms of our coefficients. We have some such terms. Now you have the average coordinate again calculated by Sapir-Whorf for expanding interval, right, is somehow oscillating. The position is somehow oscillating and increasing for the decreasing length, where it is oscillating and decreasing, and for oscillating wall where this average coordinate also somehow oscillates. And quantum force behave similarly. We have here picture again for expanding interval, contracting interval, and periodic oscillating interval, where it is again oscillating. We also try to calculate Berry phase, which is an adiabatic change of the phase of eigenfunction in the abatic evolution of the system, externally driven, which was proposed by Berry in 1984. This is in fact formula derived by Berry. However, if we put our eigenfunctions into this equation, we obtain 0. This is a Berry phase for this equation transformed to the fixed interval, yes, because otherwise it's not clear what to study. Okay. I'm going to the end. I can just tell you our conclusions. We studied the equation with modified time derivative in one-dimensional space interval of varying lengths. The equation has modified time derivative, and then the probability is conserved. We expand the solutions near suitable basis and found general solution numerically. We observe no unlimited Fermi acceleration for our model for below bounding interval. We demonstrate numerically this Zitterbewegung. Berry phase was 0 for this equation. Essentially, it's probably probably result of more or less one-dimensionality of this of our problem. Okay, and this model is at least in principle applicable in quantum optics and some condensed matter physics. So thank you. Yes.
Since you quoted the graphene nanoribbons as a motivation, you should consider also massless Dirac equation. Do I understand properly that then everything turns back into the classical Dirac equation because your V-squared mass is 0 or the same?
Yeah.
If you go to your V-squared.
Yes, I remember. Yes. For massless case, we are even able to write explicit solutions, and okay. The qualitative features are similar. For massless Dirac equation on a time-dependent interval. This equation which was there will be again massless Dirac equation. And effectively there will be only its transformation of time.
Questions? If you expand your solution in this Fourier basis and the coefficients A and tau you compute by some ordinary differential equation,
yes.
Do you have some convergence problems, or how do you discuss convergence of this series? In which sense is
I think it was tested only numerically. I don't know whether Saparboy is able to give more detailed answer because he's performed this numerics, but I think it was tested only numerically.
There's no analytic proof that there's pointwise convergence of.
See. Yes. In fact, we have such two component equations with Hermitian metrics. So this I think can be treated by known methods. You can, for example, pass to the integral equation, etc. So here it could be controlled, but the convergence of the whole series, it was tested only numerically, in fact. And, okay, in L2 it's known before, but.
Okay, then we wait for the next year conference when you will present the two-dimensional case. Most likely.
Maybe two-dimensional, also maybe something else. I should be. I mean, okay, maybe we should tell something on this particle creation effects of Casimir effect. But I wouldn't like to promise something which wasn't done.
Okay, thank you very much. If there are no further questions, comments, or remarks, let's thank the speaker again. And we have 2 minutes break for technical change.
Good morning. My talk is devoted to consideration of wave-like solution for Carteved. Oh, I can't. Sorry. Okay.
Okay, then let's start here. I'm happy to introduce Valery Zamolenko from the National Academy of Sciences of Ukraine in Kiev. And we're happy to hear something new on cognitive freestyle equations.
Okay, thank you very much. Okay. This talk will be deal with wave-type solution of Carteved freeze-type equation. I will attract your attention to KdV equation with variable coefficient and to Kamasa-Holm equation, namely, more exactly, modified Kamasa-Holm equation. Kamasa-Holm equation was discovered twice in 1980 by Focus and Fuchsteiner, the paper published in Physica D, and later in 1993 by Kamasa and Holm. This equation is generalization of well-known KdV equation as other type nonlinear famous equation. This talk contain the following part. At the first, I discuss some concepts of wave solution. Later, I explain methods of construction soliton-like solution for KdV equation. And at the end of talk, I will consider few graphs of soliton-like solution for KdV equation and soliton-like solution for Kamasa-Holm equation and Picon-like solution for Kamasa-Holm equation. Kamasa-Holm equation is famous for his Picon solution. This solution is like soliton solution except one properties. There is one point where the first derivative is does not exist. In the last, many properties of integrable system are the properties of Kamasa-Holm equation. I begin with the simple example of wave solution for equation of small vibration of the spring. In this case, we have that the solution of waves equation of this spring equation is a sum of two waves, direct waves and inverse ways. This solution, this sum of solution demonstrates so-called principle of superposition, when the influence of each terms of sum that act perturbation which acts to the equation is resulting in the sum, linear sum of each terms of perturbation. Other situation is related to nonlinear system. For nonlinear system, this linear principle of superposition don't work. But in some sense, for nonlinear system, especially for integrable system like as KdV equation, nonlinear Schrödinger equation, and other X, the nonlinear principle of superposition. It is the first point. From my point, it is important for consideration. The second point is for deducing of wave solution for KdV equation and other nonlinear equation. At present, there are a lot of paper devoted looking for of wave solution. If you open different journal, you can find a different paper connected with this topic. So I demonstrate this the way for searching of wave solution example of KdV equation. If we we're looking for wave solution, we after simple calculation will deduce nonlinear equation, the equation number two, nonlinear equation of the first order, and this equation results the soliton one-phase solution or simple solutions, simple soliton. What we understand under wave-like solution? We will understand under these terms that we will consider soliton-like solution for variable coefficient nonlinear equation. So we will construct some asymptotic approximation for nonlinear equation with variable coefficient and small singular perturbation, and this solution may be considered as wave-like solutions for consideration equation under consideration. So now a few words about concepts of soliton. The general definition of this notion may be found in book by Dresden Johnson, Soliton and Introduction. So the main feature of properties of soliton is the following. They propagate at constant speed and at the same time do not change its shapes. The speed of movements which depends on amplitude. So if we consider soliton with much more amplitude, this soliton will move with more speed, velocity than soliton with less amplitude. This nonlinear impulse in such terms used in physics is localized in space, and these objects interact like particles. So after interaction, they don't change their form. There are many examples of wave traveling solution, and now I want to remind you some example of solitons in some physical systems. So there is a short list of this example, and for example, if Huxley, famous Huxley, Hodgkin-Huxley model also possess a soliton solution. So in cosmology also is known soliton. It is maybe a presence on Saturn. So another example of wave solution is a solution of Burer's equation. It is wrong title of this slide, sorry. So this solution, and once more example of waves like wave solution gives BBM equation, Benjamin-Bonner equation, equation number 6. This equation was appeared as attempt to generalize KdV equation or to find alternative to find KdV equation. This equation, BBM equation, is not integrable equation. It possesses only 3 conservation law, but this equation possesses one soliton solution. Also, this equation don't possess multi-soliton solution. So you can see formula for soliton solution or wave solution for BBM equation. Another example of nonlinear equation that possess wave solutions are Kamasa-Holm equation, equation number 7, and modifying Kamasa-Holm equation. The difference between this equation is the square near the first derivative in x, like as for example KdV equation. Formula 9 gives soliton solution for modifying Kamasa-Holm equation. It is more complicated than in the case of KdV equation, but nevertheless, this formula presents soliton solution. So now I proceed to consideration of KdV equation. My presentation consists details description of a technique for deducing of asymptotic like solution for KdV equation with variable coefficient and small singular perturbation. I do it especially for some participants who will interested and he want to don't allow this presentation. I think that it will be possible through organizing committee. So like as in the case of a KdV equation and in the other case, we consider direct consideration of nonlinear equation and replace a constant coefficient with coefficient presented with asymptotic expansion like 11, like on 11. Under trivial assumption that the main coefficients are not equal to 0. So the corresponding form BBM equation is given with equation 12. For interesting people, you can find a corresponding publication in Journal Mathematical Physics in 2019, jointly with Yulia Samolenko. Okay. Now there is a definition of asymptotic solution and recalling of definition of Schwarz space, and next notes about the searching of solution. Because of specific feature, specific purposes of solution, we need to find a solution in this special space, special functional space. Especially this function must be, in particular case, this space G sub 0 is the space of quickly decreasing function in variable tau, in phase variable. So here it is a representation of the general form of solution, form of solution. We consider a general task of solution of equation under consideration, and we must propose some algorithm, some technique for construction of asymptotic solution, and later to estimate accuracy with which this solution will satisfy the equation. So here there is a list of points which we do during the solving this problem. We specify asymptotic solution, depends of the power of singularity. Later we deduce differential equation for regular part and singular part of asymptotic solution, and as well as differential equation to phase function, and finally we do estimation for obtaining asymptotic solution. So this general form of asymptotic solution, and the next slide is connected with description of asymptotic solution. We demonstrate techniques for particular case when power of singularity is equal to we remind with exact solution for the case of constant coefficient. In this case, we obtain graph for demonstration of form of this soliton solution, and later we consider equation for regular part. The first equation is non-linear, other equation are linear. The first equation, other equation we can solve by method of characteristics. And so the more complicated method is needed for solution of for singular terms. We consider singular terms in velocity in neighborhood of phase curve, and in this case we consider equation for the main term, and we can solve this equation in exact form. Equation number 17. You can see that this equation, this solution is like solid tone solution. In addition, this formula contains some value dependent on time variable. So there is technique for solution of singular terms of singular terms of asymptotics. We also consider question about solubility of solution 18 in special functional space. Especially, we need to have solution in space of quickly decreasing function in tau. We use this theorem, which presents a sufficient and necessary sufficient condition for solubility of solution in space of quickly decreasing function. Equation relation 22 is called the internality condition. We use this condition later while considering solubility of equation from single term of asymptotics. So first of all, we consider when the single terms belong to the space G, and the second lemma represent the condition under which the single terms represent to condition to space G sub 1. Namely, in this case, single terms are quickly decreasing function in the variable tau. And so it means that the solution under this condition will be soliton solution. All term on asymptotic soliton solution will be soliton-like function. So during consideration of equation for single attempts, we deduce the equation for phase function, and in the general case, this equation is complicated, but in simple case, under some assumption, this equation is simplified. So this is theorem about justification of constructed solution and form of asymptotic solution. This asymptotic solution is presented in a small neighborhood of curve discontinuous, and later this solution is input into space of quickly decreasing function in corresponding variable. It is another case of justification of solution. It depends on solvability of additional Cauchy problem. And now I proceed to consideration of some example. This example is connected with KdV equation. In this case, we have a nonlinear differential equation with a variable coefficient. As you can see, this equation, maybe it is impossible to find to solve in exact form. I don't know about this. So we used the technique mentioned above, and we deduced the solution for phase function before we do assumptions that regular part of asymptotic is trivial. This assumption simplified the other calculations. So the phase function satisfies the equation number 2, and its solution can be given as formula 3. As you can see, the solution is global because in general case, equation for phase function is nonlinear, and it has solution only maybe on finite interval because he is nonlinearity. In this case, also this equation is nonlinear, but this equation has a solution, global solution for all t. Necessary conditions are valid, and equation for main term of asymptotic is given by the equation on this slide, and this equation can solve exactly. And we verify that this solution belongs to the space or quickly decreasing space in variable tau. This is the graph for the main term of solution, asymptotic solution. Here is calculation needed for the second term of singular part of second singular part of asymptotics, and we find and later draw the graphs of the first order approximation for the asymptotic soliton-like solution for KdV equation for different value of small parameter, for different value of small parameter. Now I will consider another example of nonlinear system. We consider modifying Kamasa-Holm equation with variable coefficient as 18. You can see that this equation contains the set derivative like BBM equation. It contains the first derivative in T like dV and other evolution equation. And also it contains the terms with U square first derivative in X. So these coefficients are given the following formula, and phase function is equation of the simple differential equation. Its solution is very simple, and the main term of asymptotic solution is given with formula 9. You can see this solution is soliton solution, which is quickly decreasing function and is soliton solution. The next slide contain calculation needed for construction the next term of singular term of asymptotic solution, and here we have some graphs for first for asymptotic soliton-like solution for variable coefficient modified Kamasa-Holm equation for two value of small parameter. We consider epsilon equals 1 unit. Besides that, also unit of course is not small parameter, but we do choice of this value to demonstrate the graphs at this value. Here it is the first term of asymptotic solution, and finally it is the first asymptotic approximation for soliton-like solution. And the last remarks that the line on the bottom of graphs might be smooth, might be continuous, not without this discontinuous. It is some problem of construction by computer program. It is necessary to take more quality, and in this case you will receive a smooth line in the bottom of these graphs. And also here, this line in bottom and in top might be smooth. Okay. Here we have the example of Picon solution. We consider another example of another variant of variable coefficient modify Kamasa-Holm equation. This coefficient is other than in the previous example. You can see for the second terms, for example. And so we also construct for the second example the main term, the first approximation as a result. As you can see, the equation to phase function is the same. It has under trivial initial condition simple solution, and in this case we find the exact solution. Here, because of absolute value of tau in formula 13, this solution is Picon solution, because modulus absolute value of tau in formula 13. 5 minutes for me. As here there is another calculation of other terms of asymptotic solution, a few words about techniques. According to the property of Picon solution, we need to continue to consider a soliton approximation from the left side of peak and from the right side of peak, and later we conjugate this to asymptotic solution at the point of discontinuity. Okay, here we have graphs for the main term, and the top of this graph must be smooth line, must be smooth line. And here we have the first term of asymptotic Picon-like solution. Also, the bottom of this line must be smooth. And finally, we have the first approximation for the Picon-like solution for two values of small parameter. That's all. Thank you very much. Нет. Хорошо. Солитонные решения, они существуют для уравнений с частными производными с постоянными коэффициентами. И они имеют специальное свойство взаимодействия. Вот для этих построенных решений, later I will translate answer in English, okay? Для построенных решений они зависят от времени. Поэтому они уже не будут взаимодействовать так, как эти солитоны, Принцип суперпозиции уже не будет действовать. Он уже не будет действовать. Это подобно тому, как обычное нелинейное уравнение, нелинейное обычное, оно тоже уже принцип суперпозиции не действует. Okay. The question is about, is constructed soliton-like solution, is soliton or not soliton solution? I answer that the constructed soliton-like solution is not soliton solution because the main property of soliton, interaction of soliton-like particles do not take no place. On my point of view, I think that it is due to the presence of variable time in the formula for soliton-like solutions. Thank you.
Example 1, you gave the explicit solution in formula 3.3. Did you really got the solution by integrating the partial differential equation, or took you at first the solution?
Okay, moment. Example, what's formula? Okay, moment. Okay. This formula 3, yes, we solved this equation. We solved this equation 32. By hand. Yes, by integration techniques. Okay. All calculations are done by hand. Yes, I understand. You understand. Yes. Sorry, once more, maybe.
My question was whether you took this solution.
Yes.
It's a thing which you want to discuss, and then you constructed the corresponding.
Yes. We use this solution. We use this solution for constructed asymptotic-like solution. Yes. Here is function phi. This function phi is used here. Because of computer, it is easy to do.
Yeah, no further question, then let's thank those speakers of the first part of the morning session again. And we have 31 minutes of coffee break. Thank you very much. My pleasure to open the second part of the morning session with our first speaker, Roland Java from the University of Georgia, and he will speak on convolution on D groups, general Bessel potential spaces, and applications. Please, Roland.
Thank you. Well, Let me start. I will speak about Lie groups and integral equations, integral differential equations on Lie groups. As always, it's a problem to switch it off. Oh, okay. This is the content of my talk. I will remind you the definitions about Lie groups, and then I will introduce what is generic Bessel potential spaces, and we'll show you examples, several examples, and then of Lie groups. And then I will show you the applications to celebrated equations as a Prandtl equation, Tricomi equation, Lavrentiev-Bitsadze. And well, this is almost all what I want to show you. First, let me start by definitions. Well, we have a Lie group. What does it mean? We have a manifold with binary operation for pairs of elements. We have operation which maps these two elements again in the same group, and there exists unit element, and the unit element, well, neutral element, one can say also neutral, with operation with X, it gives again this X. And each element of the group has inverse element. We will concentrate on groups which are homeomorphic with Rm in this case. We will not consider the more, how to say, more complicated case when this homeomorphism does not exist, and we will consider abelian groups which are commutative. But you will see even these classes very rich to consider. Well, if we have the Lie group, then we have Haar measure, which is defined uniquely, invariant with respect to the group operation. Then we have a Fourier transformation on the group, always defined also uniquely, with its inverse, and with all properties such as Plancherel theorem, for example. And we have generic differential operators. Generic differential operators are differential operators which are defined with the help of the vector fields from the corresponding Lie algebra. We call it generic. Well, I will explain later what it's generic. Why generic? Yes. We have also convolution operators. Since we have the Fourier transform, we have convolution operators, which is written here. You see, convolution operators are just, you take Fourier transform, multiply by some function, which is called the symbol of the convolution operator, and take inverse Fourier transform. They map this function has its value in the dual group. I mean, not values, but maps is defined on the dual group, this function. And this convolution operator maps the Schwartz space of fast decaying functions to the Schwartz space of distributions. Because of the properties of the Fourier transforms, that Fourier transforms map Schwartz spaces. Fourier transform at its inverse map the fast decaying Schwartz functions and distributions to itself. That's why this convolution operator maps Schwarz space to the distributions. Okay. What is important in our case that all generic differential operators are convolutions. That's why we call it generic. They belong to the group. They are defined by the group as the generic differential operators. And their symbols are polynomial symbols. Thus, since under certain conditions or ellipticity of symbol and some additional conditions also, I will speak about it later, convolution operators are normally invertible. Therefore, we can, since differential operators and convolutions are differential operators are convolutions, you see here the equation 0,2 equation, which is integral differential equation, and it can be solved. You just can write precise solution of this equation. Inverse of this is convolution equation, and you can write inverse to it. And this has several consequences. But we need proper spaces to define these inverses and so on. Let us start by the multipliers class. Multiplier class in these groups, which we define here, coincides with the multiplier class in Rn. So we don't need much efforts to find which functions can be used as multipliers that the convolution operator with symbol A, when A is multiplied, is bounded in LP. Such conditions are when P is equal to, it's well known that due to Plancherel's theorem, that all bounded functions are multipliers. But when P is differs from 2, we have much more complicated case. Oh, yes, again, the same problem always. Oh. Why it happens? Next slide, please. Oh. Yes. Is it right? No, I think it is. Yes. Oh, yes, here is this integral differential equation, which I was speaking about it and not showing. Integral differential equation, when the generic differential operators are participating, and convolution equations. And this is all in all convolution equation with this symbol, which is written here in 0,3, which has polynomial growth. Okay? But the main thing is that it can be solved. It can be solved, such equations. Oh, too much. Yeah. Multiplier MPRN is the class of multipliers, which is same as the multipliers in classical case. Those are functions for which these operators, convolution operators, are bounded in LP. Also in our group. For P is equal to this multiplier class is well known. It is functions which are bounded. But when P is equal differs from 2, the situation is much more complicated. And if we have functions which are Fourier transforms of absolutely integrable functions, the second point here, then it is multiplier. But there are not much results known about multipliers even in classical case. In one-dimensional case, for example, all functions of bounded variation are multipliers. In multidimensional case, one can define functions which are constant on, piecewise constant functions which are constant on polytopes. Polytopes are intersection of finite number of hyperplanes, and well, then they are multipliers, and you can close them in the with respect to the norm in LP and operator norm, and you will have PCP class of functions, which is analog of of functions of bounded variation. In one-dimensional case, yes. Arise a natural question: which spaces are most relevant to consider solvability of the convolution operators? You know that Bessel potential spaces were introduced to consider differential operators, classical differential operators on domains, on Rn, and so on. But they are not suitable here for the groups. Groups have their generic differential operators for Rm are coordinate derivatives. So for them, I just speaking, but okay, next slides. We should introduce here generic Bessel potential spaces. Why generic? It's in pharmacology. Generic are the medicines which are produced by other firms than the original firm. So it's so here there is the original definition of Bessel potential spaces in Rn, and on the groups we call it generic because it's not original. Yes. Well, definition is the same. You just take, instead of classical Fourier transform, you take the group Fourier transform on the group. You take the symbol 1 plus xc square in power s, oh, sorry, it should be s half there, s half, and take the convolution operators with this symbol, apply to the function, and it should belong to LP. And that is the definition of generic Bessel potential space, HSP. Definition is absolutely the same. What it gives for Sobolev spaces? You know that Sobolev spaces coincide with Bessel potential spaces for integer values of the smoothness parameter S, when S is M is the integer. Same here, but here generic differential operators define Sobolev spaces. You apply generic differential operators up to order M to the function, and they all should belong to LP space. Then you have a generic Sobolev spaces, and they coincide with generic Bessel potential spaces for these integer values. Okay. Then if we have such definition, very naturally, Bessel potential convolution operators are bounded in Bessel potential spaces. We should take into account order of the operator, I mean order of the symbol, which it has at infinity. And then everything is okay, as in usual case of classical Bessel potential spaces. Then multiplier class, MPR, it consists of the functions c in power r, here it's written correctly. Here it's written correctly. The multiplier class is defined as usual multiplier, LP multiplier class multiplied by this function. Well, and then it is a class for which the operators, convolution operators, are bounded from HS to HS minus R. Okay. Now about now theorem. Yes. T is between 1 and infinity. S is arbitrary real number. And we have a convolution integral differential operator, which I showed you. And the symbol belongs to MPN. Then this equation is for the solvability of this equation, it's necessary that the symbol will be elliptic. Ellipticity condition is 0,6. 0,6 gives you ellipticity condition of the symbol but it's necessary condition. Sufficient condition, it's not sufficient condition. Sufficient condition, it becomes if A is in PCP or A is Fourier transform of L1. Why? Because of Igari paradox. On the next slide, I will show you. And now about spectra. We can say that the spectra of this operator is, is essential spectra. It has only essential spectrum. And this essential spectrum coincides with the image of the symbol. Image of the symbol. And what is the Igari paradox? Igari paradox is such that there exist continuous multipliers if P differs from 2. For 2, it does not work. If P differs from 2, there exist continuous multipliers such that the operator, convolution operator with this continuous symbol is bounded in LP. This multiplier is elliptic, but the inverse is not bounded in LP. Inverse is not bounded even for continuous function. So this condition ellipticity is not sufficient. It's only necessary in general case. And theorem 2, we can write explicitly fundamental solution of our differential operators. Fundamental solution is written in this way. You have the operator, you take its symbol, invert its symbol, takes the inverse of the symbol, 1 divided by the symbol if it is elliptic, and consider the convolution operator with this symbol. And the kernel is the fundamental solution. Or one can say so. You take the inverse Fourier transform of the inverse function. It gives you fundamental solution. And it is, since it is polynomial, to calculate explicitly such fundamental solution is not very much complicated. But if you have a fundamental solution, you can develop the whole potential theory on the groups and solve the boundary value problems and so on. Yeah, if symbol is not elliptic, it can be done by approximation. Okay. Now, examples. Euclidean space is the most trivial example of Euclidean of the group. Yes, I will do. Yes, here it's written about fundamental solution. Euclidean space, RM. Euclidean space with respect to the sum is a Lie group, and you know everything is classical here. Generic differential operators are classical coordinate derivatives. Fourier transform is classical Fourier transform, and everything, the convolution is classical convolution with difference in the kernel of integral operator. The last formula on this slide. Okay. Another example on the half-line. The half-line is also a Lie group with respect to the multiplication. And the Haar measure is here Tx divided by x. Yes. Tx divided by x. And generic differential operator here is derivative followed by multiplication with independent variable. This is the generic differential operator. Yeah, and Fourier transform is the Mellin transform. And the convolution is, again, convolution, but not with difference in the kernel, but the ratio of arguments in the kernel. So everything is classical, it's well known. Next example is relatively new. Next example is example that -1,1 interval is group. It is group with respect to this multiplication written here. This multiplication makes -1,1 group. And our measure is the x over 1 minus x squared. Well, no, it has all properties. A Fourier transform is written here, formula 09 for Fourier transform. The dual group is again here. We can take direct product of -1,1, and it is also Lie group, of course, but I take for simplicity one-dimensional case. Yes. Inverse Fourier transform is written formula 010. Convolution equation you see here, it has a bit complicated form, but it is convolution. And if you apply to it the Fourier transform, it becomes multiplication. So it's really convolution equation. And the generic differential operator is 1 minus x squared dx in this case. So it has singularity at the end of, Haar measure also demonstrates singularity at the end of the interval, -1,1. Okay. Now about application of those equations, where everything started from. I will tell about this a few slides later. A Prandtl equation, very well known. Airfoil equation or Prandtl equation, it has many applications, especially in aerodynamics. This Prandtl equation turned out to be convolution. Convolution on the interval -1,1. And the symbol is written here, 012, is the symbol of this convolution operator. Okay, and the solution can be written, since we have symbol, we can take 1 over this symbol, and convolution operator with this symbol is the inverse to this operator. So inverse is written. Prandtl equation was studied by many authors. Me and Mazia also have written paper about it about 40 years ago. Many people wrote papers about Prandtl equation, but nobody solved it. It was solved numerically, investigated Fredholm properties, and so on, and so singularities. And now we have the solution of this equation, exact solution. Here is the spectra demonstrated. It's a line, vertical line, is the spectra which crosses the real line at the first coefficient C, where this first coefficient is. Yes, this is the spectra. Okay, next equation, celebrated equation also, is Tricomi equation. Tricomi, and then also the next equation will be Lavrentiev-Bitsatze equations. They come from boundary value problems for the mixed type differential equations in domains. Yes. Sorry, thank you. Yes. This is a Tricomi equation. You see, it contains singular integral operator and also operator with fixed singularities. 1 minus xy has singularity when x is equal y and is equal 1 at the endpoints. So nevertheless, this turned out to be also convolution equation on the interval minus 1, 1. Here is written this symbol in formula 015. And here, again, of course, you can write is written already the inverse to it. And here is the spectra of this operator, which is in the first case, spectra was unbounded because it was integral differential operator, Prandtl equation. But in this case, spectra is bounded, and essential spectra is it's only essential spectra. It depends on the coefficients, of course. And the last example in this series is the Laurentiev-Bitsadze equation. Laurentiev-Bitsadze equation, it's also a singular equation, and the symbol is written here. It's a rather simple symbol. Inverse can be written quite easily. And the spectra is this vertical interval, essential spectra of this operator. And well, how this work happened at all with Petrov and Suslina, later Suslina joined him, made such transformation, which is written here, of the interval minus 1, 1, and brought those equations, which I named these three equations, to the axis, minus infinity, infinity, and find that they are convolutions. When I saw it, I understand that there should be some group structure. And I find this group operation, and everything is written in the group. And what followed, we were able, with my colleagues, Rozhansky, Cardona, and Hendricks, to find many examples of groups. I will only show you groups and without details. Any cones in Rn also. Here is only two-dimensional case. Any cones with carved surfaces or straight surfaces. Yeah. Sorry. Yes. Oh. Yes. Oh. I was so behind. This is the group operation you see here. Yeah, this is the transform which Petrov and Suslina used to reduce Prandtl equation and the Tricomi equation to the axis, find this convolution there. And we find the group structure. And the next slide is that we find many examples. Here are carved cones, straight cones. And for us was surprising that any star-shaped domain in Rn is also Lie group. Can be found all these Fourier transforms and generic differential operators, everything. Well, of course, these cones, two-dimensional, and pyramidas, double pyramidas, and also tubes, carved tubes. They are all Lie groups. Can you introduce Lie structures there, group structures there? And what is the last slide here? Me with Duan Cardona, Hendricks, and Mikhail Rozhansky write also a paper about global pseudo-differential operators on the Lie group G. It's not published, but submitted. Thank you for your attention.
For one question which leads to a short answer. Yeah, please.
Definition of generic in your work? short question. So the generic operator is definition given in your or it's well known in the theory. Generic operator.
Can you speak a little bit louder?
Maybe we will speak about
Label.
during the break.
Okay.
Thank you.
Yeah. So we have to go on in the program. Then thank you again.
Thank you.
Is Akramov from the National University of Uzbekistan, Tashkent, and he will speak on spectral properties of branched nanoscale lattices. Please.
Thank you for the introduction. Today I'm going to talk about the spectral properties of branched nanoscale lattices. This talk is based on the recently accepted manuscript, and this work is done with in collaboration with Professor Karsen Tronk, Jambol Yusupov, and Professor Davron Matrasulov. So my talk is outlined as shown here. After the motivation, I'm going to talk about the discrete Schrödinger equation in a chain and the exact solution of this equation. Then I'm going to briefly talk about quantum graphs. Then I will proceed to the main task, which is called the branched lattices. Then there will be some conclusions. So why branched lattices? Many systems arising in condensed matter have discrete structures, particles, and waves in such systems, which are the carriers of charge, energy, and signal wave in quantum region. Conducting polymers, which are the basic functional materials for organic, electronic, and thin film photovoltaics, can be considered as quantum lattices. So let me show the discretized version of the Schrödinger equation without any potential, that is for a free particle. This equation is derived by using the standard finite difference method for the second order derivative here, where here A, small a is the step size. Now let me show an exact solution of this equation, which is shown here. Here G plus minus A is given by these relations. Now let me show the continuum limit of the solution by simple calculations. Here we have defined the z plus minus function here. Then taking the limits of this G plus minus A function leads to the following expression. Then simple calculations yields to the wave function to this expression, which is the same with the the solution of the continuous case. This limit is obtained for a fixed point alpha here. Now let me present the graphical representation of the of converging the solution to the case of the continuous to the solution of the continuous case. Here is different colors correspond to the different values of the step size, and the red and the black line correspond to the solution of the continuous case. While decreasing the step size A, we can easily observe the converging of the solution to the continuous case. Now, in this work, we have showed we have imposed the two types of main boundary conditions. The first boundary condition is called the Dirichlet boundary condition, which is shown here. And we have considered the discrete interval from 0 to L And Dirichlet boundary condition is imposed at the boundaries of the interval, and substituting the solution to this boundary condition yields to the set of equations, set of linear system of equations, and eliminating capital N, A, and B leads to the following secular equation. Before solve this secular equation, we little bit analyze properties of the G plus minus function, which is given here. The main property of this G plus minus function is its absolute value is equal to 1, and calculations yields to find the eigenvalues Km in terms of A and capital N. Here, M is the integer number. The next boundary condition is called the Neumann boundary condition. Before that, let me show the continuum limit of the eigenvalue at step size tends to 0. Then the calculations show the eigenvalues, which is the same of the eigenvalue in the continuous case. So next boundary condition is called the Neumann boundary condition, which is shown here. Again, we used the standard finite difference method for the first order derivative here. Again, substituting the solution to the boundary conditions yields to the set of linear homogeneous equations, and again, eliminating capital A and B yields to the following equation for finding the eigenvalues. Again, we use the properties of the G plus minus AA function to find the eigenvalues. Then we come to the eigenvalues for the Neumann boundary condition. The difference between the Dirichlet boundary condition here is -1. And also simply show the limit of the eigenvalue at step size A tends to 0, which is the same eigenvalues in the continuous case. Here you can see the tables for the eigenvalues. The first column corresponds to the continuous case, then the other columns correspond to different values of step sizes. The upper table correspond to Dirichlet boundary condition, lower table correspond to Neumann boundary condition. You can easily observe while decreasing step size A, the eigenvalues converging to the continuous case. So now let me briefly talk about quantum graphs. What is quantum graph? Quantum graph is a set of edges are connected in terms of some rule. This rule often called the topology of the graph. In these figures, you can see the different types of quantum graphs. From a mathematical point of view, topology of the graph can be defined in terms of its adjacency matrix, which is shown here. If A and G vertices are connected, its element is equal to 1, otherwise is equal to 0. In order to solve the Schrödinger equation on the graph, we need to write the Schrödinger equation on each edge of the graph, which is shown here. Then we have to define the Schrödinger operator on the graph, component-wise on each edge of the graph, which is shown here. Schrödinger operator is a self-adjoint operator. This phenomena can be proved introducing the scalar product on the graph, which is shown here. The scalar product is equal to the sum of the scalar products on each edge of the graph. Then one should write the skew Hermitian here. Then calculations yields to the expression for the skew Hermitian. Now one should write the boundary conditions at the vertices of the graph. The first boundary condition comes from the wave function continuity, which is shown on the first equation. Then the second type of boundary condition is called the current conservation rule. For any real values of lambda I, Schrödinger operator is self-adjoint with these boundary conditions. So the next, we can easily write the solution of the Schrödinger equation on each edge of the graph. Substituting this solution to the boundary conditions leads to the following set of linear equations. Then again, eliminating the capital A and B leads to the following equation to find the eigenvalue K. Actually, this MK matrix has the same of the following. Here, capital E is the number of edges and capital V is the number of vertices. Now, let me consider a simple example, which is called the quantum star graph. Here, we consider the star graph with three finite edges, and its adjacency matrix is shown here. And here, boundary conditions on each vertices are written. Then substituting the solution to these boundary conditions leads to the following system of equations, linear equations, and we can explicitly write the MK matrix, which is shown above. Here, entries of MK matrices are the following. Let me proceed the main task before showing the values of the eigenvalues. Branched lattices can be considered as a quantum graph with discrete edges, and adjacency matrix is the same with the continuous case, and wave function is a e-component vector, and each component is a vector which is shown here. And discrete Schrödinger equation is written on each edge of the graph, which is shown here, and discrete Schrödinger operator is also the self-adjoint. To prove the self-adjointness of the discrete Schrödinger operator, one needs to introduce the scalar product, discrete version of the scalar product, which is called the Euclidean inner product, which is shown here. Then here, discrete Schrödinger operator is written component-wise on each edge. And the skew Hermitian can be defined as the same with the continuous case, and the calculations yields to the following expression for the skew Hermitian. Then one needs to find the boundary conditions that this skew Hermitian will be equal to 0 in order to be self-adjoint of the discrete Schrödinger operator. Similarly, we choose the current conservation rule in the first equation, and then the discrete version of the current conservation is shown here. Here also we use the standard finite difference method for first order derivative. Again, for any real values of lambda I, discrete Schrödinger operator will be self-adjoint with these boundary conditions. Then the solution of the discrete Schrödinger equation on each edge can be written in this equation. Here, G plus minus AIG shown here. Then continuous limit of the solution at step size tends to 0 for a fixed point. It's shown here. This limit is the same with the continuous case. Substituting the solution to the vertex boundary conditions leads to the following set of linear homogeneous equations. Again, we eliminate A and B from these equations, then we come to this determinant equation. The structure of this matrix MK is the same with the continuous case. Now, let me consider the discrete version of the star graph, which has three finite discrete edges, which is shown here, and the adjacency matrix is also the same. Then we rewrite the boundary conditions on each vertices on the star graph, and substituting the solution to the star graph leads to the following system of linear equations. And we define the structure of the MK matrix here with entries are the following. Now let me show the eigenvalues of the discrete and continuous Schrödinger operator. In the first column, you can see the continuous, you can see eigenvalues for the continuous case, and other columns represents the discrete version of the problem. These columns corresponds to different values of step size, and while decreasing the step size A, the eigenvalues converging to the continuous case. Now, let me conclude my talk. An exact solution of this great Schrödinger equation in a chain is obtained. Consistency of the result with the continuous case is shown by computing the continuum limit of the solution. Exact eigenvalues for the star graph are obtained. Extension of the approach for arbitrary graphs is also presented by deriving general solution and secular equations for finding the energy eigenvalues. Let me mention our collaborators. The first collaborator, Professor Carsten Trunk from Institute for Mathematics from Ilmenau, Germany, Jambul Yusupov from Kimya International University in Tashkent, and Professor Davron Matrasul from Turin Polytechnic University in Tashkent. Thank you for your attention.
Very much for your presentation. The discussion is open for questions, remarks, comments. A lot of discrete Fourier analysis also behind to compute all your eigenvalues and so on.
Yeah.
Do you use also numerical algorithms?
Yes. While calculating the eigenvalues.
For instance, yeah.
Yes, here. To solve this equation, we have used simple numerical calculations because it cannot be solved analytically.
Is it a Fourier type algorithm?
No, no. This is just a simple numerical calculations.
Okay. Any other question, remark? If not, then let's thank the speaker again. And we have minutes today.
That doesn't continue. I don't think that sometime comes in 10 minutes.
Okay, the big boss urges me to immediately to continue. Clearly, I have to follow this duty, and then we go on with the talk of already mentioned in this talk here is a change of the program of Jambul Yusupov from the Kimya International University in Tashkent. And here It's the title of this talk, Modeling Reflectionless Propagation and Vector Solution in Networks. Please.
Thank you very much for the introduction. So, first of all, I would like to thank organizers and Somparty team for organizing such a nice conference and inviting me to give a talk here. It's my pleasure. And today's talk is one of the works, series of work on topic transparent boundary conditions for evolution equations on branched structures. And the title is Modeling the Reflectionless Propagation of Vector Solitons in Networks. This work is done jointly with Matthias Erhardt from Wuppertal and Davran Matrasulov from Turin Polytechnic University in Tashkent. Also, it should be noted that two persons more, Mashrab and Karim, is also involved to this work. Well, let me start. And this is the outline of the talk, and I will first. I would like to start with giving some definition and explaining the concept of transparent boundary conditions. Then to show how to derive the transparent boundary conditions for Schrödinger equation. Then we extend this problem to the Monakov system, and the main part is the transparent nonlinear networks, which modeled in terms of Monakov equation on metric graphs. And at the end, I just summarize my talk. And yeah, the transparent boundary conditions. In the mathematical point of view, the concept of transparent boundary conditions for an evolution equation implies that its solutions in the finite interval are equivalent to those in the whole space restricted in this interval. And in the physics point of view, the transparent boundary conditions implies reflectionless transmission of waves through these boundaries. Well, in my opinion, to explain and to the easy explain of the transparent boundary conditions can come from the wave equation. So this is wave equation, and it can be factorized as shown here. And by separating outgoing from incoming waves, by defining these two new functions, okay, for some L on the right half line, we have the general solution in this form, yeah? Where psi and phi are arbitrary functions determined by initial and boundary conditions. So for incoming wave at the boundary, we have this one. So since no incoming waves in the right half line, so we have V equal to 0 at this point, and then thus transparent boundary conditions at this point is nothing else but this. It means that, yeah, the factorization of the equation of the can easily show us the transparent boundary conditions. So now let me proceed to the derivation of transparent boundary conditions for Schrödinger equation. And here we consider time-dependent Schrödinger equation with some initial condition. And here the goal is to design transparent boundary conditions at two points 0 and L, such that the resulting initial boundary value problem is well posed and its solution coincides with the solution of the whole space problem which is restricted in this interval. Yeah, the two basics, two weak assumptions here is in order. So that is the initial data is supported. We assume that it's compactly located supported in this interval, and the given potential is constant outside this finite domain. And the construction idea, which belongs to this authors of this paper highlighted in this slide, implies that we divide the whole space in three parts, these three sub-problems, interior and two right and left exterior problems. And here we see that we assume that our initial condition compactly supported in the computational domain, the interior domain. Okay, and now we for the interior problem we can state the problem as shown here, where T0 and TL is still unknown operators, which denote the Dirichlet to Neumann maps at the boundaries. And we also, so these operators are obtained by solving the two exterior problems, left and right. Yeah, and using the Laplace transformation, the exterior problem is transformed to this, and general solution for this transformed equation can be written in this form. Since its solution have to decrease as x goes to infinity, we obtain this solution. And hence the Laplace transform Dirichlet to Neumann operator is, of course, we can also calculate analogously for T0 the same. And an inverse Laplace transformation yields to the right TBC at the point x equal to L. As you can see here, it's a very complicated expression for the boundary conditions. And it's obvious that they arise from the factorization of the Schrödinger operator, as we did it for the case of wave equation. And here this term, yeah, this term is nothing else but fractional half-time derivative. Okay, now we consider transparent boundary conditions for the Monarch system on a line. Before, what people do usually when they consider the branched structures, they first should solve the problem for the simple case, say line, and then we proceed to we extend this problem to the network case. So the Monarch system is the coupled system of nonlinear Schrödinger equations, and the solution is the vector, two-component vector. We use the potential approach here, so-called potential approach. So the Monarch system is formally reduced to the system of linear PDEs here, where the potential is written in this form. It's formally. Now we introduce the following new vector functions, V and where nu is calculated taking here partial derivatives, we obtain these expressions. Then we get this operator L, and by linearizing this equation using pseudo-differential operators calculus, we have this expression where lambda is the principal symbol of the operator, the big lambda. And we obtain the following system of operators, which yields the symbolic system of equations. And this, from here, we can see that we have the expression which is written in, which is just approximation of transparent boundary conditions. And the asymptotic expansion in the inhomogeneous symbol is defined in this way. So I want to, in order to save some time, I just skip the technical calculations and just wrote here the first order approximation for the left and right transparent boundary conditions here. And this is the first approximation, first order approximation. Also, in our work, we restricted ourselves till the second order approximation here. And then we showed that it's reliable with by showing numerically. So for this, I mean, in the sense of numerical approximations, it's enough to consider only the second approximation. Here we use the so-called leapfrog finite difference methods shown here. And also we discretize the potential term in terms of the values of the function. Of course, this leads to the following explicit finite difference scheme, where U is the two-component vector. This is the discretization of the equation itself. But except this, we also need to discretize the obtained transparent boundary conditions. And we do first approximate the fractional differential operator shown here by using this sequence shown in, I mean, the betas. Yeah, we also discretize function nu using some trapezoidal rule, and then also get the exponent discretization of the exponent of I nu. Okay, the values of the wave function at the right boundary can be obtained by solving the system of nonlinear equations shown here, and this gives us the values of at the boundaries, which is the transparent boundary conditions. So we can show this by numerical simulation, and as initial condition, we choose here the single soliton, which is the exact solution of the Monaco system. And the system parameters is shown here. So we take L equal to 40 and so on. And in this plot, you can see that the right traveling single soliton is goes to the right boundary and just disappears because of the transparency of the boundaries. We can also calculate the energy within this interval. And yeah, it should, of course, disappear over time. And this can be seen from this plot. So this is the time evolution of the soliton energy in the interior domain. And it's disappeared. It goes, it's vanished after 15 years. So another quantity which is interesting here to calculate is the absolute error, which includes both errors, which is comes from the error of discretization of equation and the boundary conditions. And here you can see this. The blue line is discretization error, which comes from the discretization of equation, and the red one which has both. And you can see that the most the part of the error is due to the boundary conditions, because it's first of all, it's approximation of the transparent boundary conditions, and moreover we discretize it. Okay, so now let's proceed to the next. The main part of this talk is the transparent nonlinear networks, and here we use as a model we use the metric graphs to model the networks, and we consider yeah, of course, there are some motivations why transparent nonlinear networks are interesting. So the effective signal transfer in optical fiber and optoelectronic networks can be modeled by nonlinear networks. Tunable charge transport in branched nanostructures, tunable charge transport in conducting polymers, effective spin hit and quasi-particle transport in low-dimensional structures arising in condensate matter can be examples of where can we use this model. And the goal here is to develop some approach to avoid the direct use of TBC, which has the very complicated form expression at the vertex, but turning the vertex boundary conditions equivalent to a TBC. And combining the concept of transparent boundary conditions and quantum graphs to design the vertex boundary conditions, providing the reflectionless transmission of waves through the graph branching points. And in the following such graphs, we will be called the transparent graphs. Now let's consider the Manakov system, which is given in two component, which is just two component couplet nonlinear Schrödinger equations, and the domain, for the sake of simplicity, we just consider 3-bond star graph. And you know that the star graph can be considered as the building block for any kind of graph. So this is important. And so we denote psi j as this is a vector, 2-component vector, and the set boundary conditions given in this form, which is weight continuity and generalized Kirchhoff rules, where we introduce some non-zero real constant alphas. And without loss of generality, we can assume that this alphas is just the square root of beta j, where beta j are non-linearity coefficients of the system. And by doing this, actually, we connect the boundary condition parameters with the system parameters, which is important in the experimental point of view. It can be. So again, using the so-called potential approach, we use it in the case of linear, the problem on a line, and applying these boundary conditions shown here, we come to this result, and the boundary conditions, these boundary conditions coincide with the 1D case when this factor is equal to 1. It is this one here. So we here we have factor, and in order to have these boundary conditions, which is transparent for the first bond in the case of star graph here, it should be equal to 1, and this shows that we have some constraint in the form of some rule when it fulfills with respect to the nonlinearity coefficient. So we have transparent reflectionless transport of waves in such a domain. Yeah, we can make some numerical experiments to show that it works actually. And here we take the initial conditions in the form of such function here, and it's compactly we suppose that it's we assume that the initial condition compactly supported in the first bond, and we have nothing in the other two bonds. So the explicit midpoint rule is used here. This is the same as in the line case, and with these parameters. So the calculations show that the dynamics is here totally ballistic without any reflection. And the graph here shows that for fixed beta 2 and beta 3, we can find this is a dependence of reflection coefficients on parameter beta 1 when the beta 2 and beta 3 is fixed. And here we can see that when the sum rule is fulfilled, we have reflection equal to 0. Okay, and now let me summarize my talk today. So the transparent boundary conditions for the Manakov system is derived within this work. An effective discretization for the transparent boundary conditions and its implementation is presented. The absence of backscattering for Manakov soliton when TBCs are imposed is demonstrated by a numerical experiment. The concepts of transparent boundary conditions is applied to the Manakov system on metric graphs to model the reflectionless transmission of vector solitons through the graph vertex. It's also shown that for the case where the nonlinearity coefficient satisfies the sum rule, the vertex boundary conditions in terms of weight, continuity, and Kirchhoff rules become equivalent to the transparent boundary conditions. And the reflectionless transmission of solitons through the vertex of a graph, star graph, is shown by solving the problem numerically. And the potential applications can be shown here is the modeling the tunable transport of Manakov solitons in optical media and for optimization problems of optical devices where such solitons appear as signal carriers. Transparent optical fiber networks, ballistic particle transport in branched nanostructures and nanoscale networks. Also, ballistic transport of charge carriers in branched conductive polymers can be examples of potential applications of such models. Thank you for your attention, and if you have questions, please.
Doors open for questions, discussion.
Yeah, Jean-Paul, in the first part of your talk, in the first section, the potential was constant, right?
Yeah.
But this is not necessary, right? Or why do you choose it to be constant?
Actually, it's to get the explicit form of the.
Yeah, okay.
Yeah. Of course, it can be solved for any kind of potential, but it will be just approximation. Like in this case.
Yeah, but transparent boundary conditions you can give. Transparent boundary conditions you can give in form of the DFT to Neumann method, right?
Yeah.
Other questions? If this is not the case, then let's thank all speakers.
Thank you.
And the session is closed and we meet again at 3 o'clock in the afternoon. Thank you very much.
We start the afternoon session, and the first presentation will be Evgenia Simonova from the Institute of Mathematics in Kiev, Ukraine. He has co-author, let's say, the Solodkin, who is from the University of Pisa. And Evgenia will speak about Chebyshev polynomials for solving numerical differentiation. Please.
Thank you for introduction. And yesterday we presented our joint research with Jürgen Pristin, and today I would like to present our research with Sergei Solodky. And the topic of our research is a truncated Chebyshev spectral method for solving numerical differential and summation. And, sorry, doesn't work. Oh, it works. Thank you. And also a small introduction. As you know, the derivatives is one of the most important concepts in the calculus. And it is well known that derivatives are used to describe how a function changes. And in many particular problems, the understanding of most physical phenomena involves the determination of derivatives of original function. But however, numerical differential techniques are not often used by engineering. Why? The reason is that the numerical differential problem is an ill-posed problem in the sense of Adamara, which means that any small error in the measurement may cause a huge errors in the numerical approximation. But as you can see in the slide, derivatives is used in many fields of mathematics and applied mathematics. And we just mentioned here some possible application, but it is not all. I think you can read this, a lot of problems that we can solve by numerical differential technique. And here my short explanation, what does it mean numerical differential is ill-posed problem. So if we take some function f, some continuous functions with one derivatives, and we perturbed a little bit this function in the following way. And if we take a first derivative of such function and measure measure the error between the function and perturbed function, will be delta. But if we measure the error between first derivatives and first derivative of function and first derivative of approximation, we obtain a big quantity. Yes. So if n equals to infinity, this error can be increased uncontrollable. So it means that the problem is ill-posed. And also the short introduction or short example, numerical differential can be reduced to the solution of the first kind of integral equations. For the first order derivatives, it can be reduced to the solving of Volterra equations, as you can see here. And for the second order derivatives, it can be reduced to solving of Fried-Golomb equations of the first kind. And the first paper, where numerical differentials was considered like ill-posed problems, was done by Dolgopolova, Ivanov, and Ram. In the first paper, you can find converges of a numerical differential algorithm. And in the second paper, you can find the converges with the rate of numerical differential algorithm. And this is the first paper where our problem was considered like ill-posed problem. I'm sorry, it doesn't work. Maybe the next slide. Yes. And so all methods for numerical differential, we can divide it on two groups. The second group is a classical Tikhonov type of regularization. So in this group, we apply some standard regularization technique. And it can be standard Tikhonov method or iterated Tikhonov method or Lavrentiev method and many, many others. And the paper related to this topic, you can read here. And I also would like to mention some disadvantages of this method. And this method leads to solving integral equations, as I demonstrated above, yes? And most of this method requires solving a system of equations. And also this method requires to select two parameters, regularization and discretization parameters. So this is our disadvantages of this group of methods. And also we have another group of methods. We call it self-regularized method. And self-regularization consists appropriate choosing of discretization parameters, only appropriate choosing of discretization parameters. And in this case, discretization parameters play a role of regularization parameters. And so we need only to discretize our problem with the appropriate level. And the following paper, you can find some additional information. And also, I would like to demonstrate, to discuss a little bit more about the self-regularized method. We call it truncation method for numerical differentiation. And let's see, what is it? So we would like to approximate the R derivatives of function f. And our method, we noted D with big N. And our method consists in replacement of a full Fourier series by the finite analogies with the appropriate level n. Here, yes, this is. And here we need some orthonormal basis. And as such orthonormal system, we can choose some systems that satisfy certain assumption. But the first paper where such a method was proposed for numerical differentiation is a paper Shuai-Lu, Valeria Naumova, and Sergei Pereverzev. And here Legendre polynomial system was proposed as such orthonormal basis. And they obtain a zero accuracy for recovering of first derivatives of the function. And I would like to formulate our aims and of our investigation. So we would like to construct algorithm that achieves the optimal order of accuracy by using the minimal amount of discrete information in the form of perturbed values of Fourier-Chebyshev coefficients. And we would like to determine the condition under which the numerical summation problem is well posed. And also to provide efficiency of our method, we would like to conduct some numerical experiments. And now we are ready to state our problem. So at first we introduce the system of Chebyshev polynomial. Here I take orthonormal system of Chebyshev polynomial, and it is some standard wave for this system. And also we need some class of function, and so by L2 with omega we denote the integral function with some weight W, and this space of functions supplied by the following scalar product and norm. And also we need a space of continuous function S, C, on continuous functions on interval -1, 1. And also we will need a space of sequences, small LP, with some P bigger than 1. And also we will need a space of smoothness for our function, and this space of smoothness we introduce in the following way. So we will assume that our function f satisfies the following relationship. So it should be less than infinity, and you can see that here our perturbed our Fourier-Chebyshev coefficients summable with some multiplier here, and here the parameters S and parameters mu is some parameters that some smoothness parameters. And as I mentioned above, numerical differentiation is is ill-posed problems, but it is ill-posed problems in the case of perturbation in input data. And so we assume that our data is Fourier-Chebyshev coefficients. We assume that such information are given with some perturbation, and on this perturbation has the following assumption, and here we measure our perturbation in the space small LP. And also we would like to state our problems in the framework of ABC theory. So we would like to know the informational complexity of our problem. And let omega be some arbitrary domain of coordinate plane, and omega is an index of our Fourier-Chebyshev coefficients. And by cut of omega, we mean the number, how many this perturbed Chebyshev coefficient we need. And by information vector G, we will take the set of perturbed values of Fourier-Chebyshev coefficients. So here we introduce omega and information vector G. And I also recall you that as information about our problem, we take a Fourier-Chebyshev coefficients. Fourier-Chebyshev coefficients, this one, yes. And by numerical differential algorithm, we mean any mapping, small psi r, that correspond to the information vector, some element from the space psi. But the space we mean L2 space or C, the space of continuous function. And the set of such algorithm, the set of all such algorithm, we will note by big psi. And now we are ready to introduce the hero of our algorithm in our class of smoothness. And this is hero has the following form. Here the hero accuracy between our R derivatives and our algorithm, and we take a supremum. We take a supremum over all possible smooth function, and supremum over all possible perturbation of such function. So, and we will note such quantity by hero of the algorithm. And now we are ready to introduce our main quantity, the minimal radius of Galerkin information. And this minimal radius you can see here. And here we take the hero of our algorithm, and we take infimum over all possible sets omega and all possible algorithms that use information vector over omega. And such statement of the problem is a classical statement for the informational best complexity theory. And minimal radius Galerkin information describes the highest accuracy that can achieve our method when it use perturbed Chebyshev coefficients like discrete information. And so I would like to describe our truncation method. And here our derivatives are what we would like to approximate. And our truncated method has the following form. I think it is very easy. And omega is all integers numbers that from the following interval. And let's consider the error of our truncation method. The error of our truncation method can be divided into two parts. The first part, this is here. As you can see, there is no perturbed function, and the first part describes the accuracy of our truncation method. And we found also the bound of this quantity, and it is the following. And as you can see, these values tends to 0 if n tends to infinity. And the second part of our error, it is here. You can see, and we call this part stability. It describes the stability of our problems. As you can see, these values tends to infinity if n tends to infinity. So the essence of our problem is to find some points where our accuracy will be the best. So we need to balance these two curves. And our results, what we obtain, so if our function f is smooth enough, so if it belongs to our class of smoothness with some assumption on the parameters, and our discretization level is the following. We obtain the following error of the accuracy. This is for a uniform metric. This is a error for uniform metric. And as you can see, the card, so the quantity of our perturbed Chebyshev coefficients is the following. And in the integral metric, we have a similar approximation error, but it is natural that in integral metric our error approximation a little bit better than in uniform metric. And here, for this better approximation, we need the same quantity of perturbed Fourier Chebyshev coefficients. And also we found order bounds for the minimal radius of Galerkin information. We found a minimal radius Galerkin information for the C metric and the matrix L2, and it is the following. And as you can see, if you compare it with our results, our method realized this order optimal bounds. It proves that our method is order optimal, and all method in this class of method cannot have accuracy better than what we state here. And so some comparison. If we take our function f with our smooth function f, so for some certain parameters, we compare truncation method for Chebyshev polynomial and truncation method for Legendre polynomial. And you can see that for Chebyshev polynomial, we have a little bit better order of approximation than for Legendre polynomial. And also, I would like to discuss a little bit separate about the summation problem. And what does it mean, summation problem? We need to sum our Fourier coefficients, perturbed Fourier coefficients. And it looks like this summation problem looks like formula 7. And we also found minimal radius of Galerkin information for the summation problems, and it will state the following order of the bound. And for the C metric, for uniform metric, and for integral metric, we also found the following estimation. And And our summation method realizes optimal bounds. And it is very interesting, the corollary from this theorem. It's turned out that for some certain parameters, the summation problem can be well posed. And it's turned out that for p equals 2 and any parameter c bigger than 2, the summation problems in integral metric is well posed. And it also means that in any weaker metric, our problems can be also well posed. And in the metric of uniform metric, in uniform metric, for parameters p equals 1 and c bigger or equals 1, our summation problems is also well posed. But even in this case, it is necessary to adjust the levels of discretization and anti-perturbation delta to prevent the saturation effect. And as I promise you, we have done some numerical experiment to demonstrate effectiveness of our approach. And the first, we take the function f1. This is a following function with some certain parameters, mu and s. And we perturbed our data with some random noise. It was done something like that. And what we obtain, we recover the first derivatives and the second derivatives for the different perturbation, and we take perturbation of order -4, -5, -6, yes. And what we obtain the zero and L2S, you can see here, for the first derivative and for the second derivatives, and as you can see, the order of accuracy for second derivative a little bit worse than for first derivatives. And here by n, this means how many perturbed Fourier-Chebyshev coefficient we need to realize our method. So it's for the first case it's 6, for the second it's 9, and for the third case it's 12 Fourier-Chebyshev coefficients we need to realize our method. And also some pictures. You can see the first case, the second, and the smallest perturbation, we have the better approximation. Yes, and this is what was for the first derivatives, here for the second derivatives, and the second example here, and we take a model of the function, but for the model of the function, we can only consider the summation problem, because it is the smoothness of this function doesn't enough to consider the differentiation problem. So here you can find a result for summation with random noise for our model of our function. And also, as you can see here, we need more perturbed Chebyshev Fourier coefficients. And also picture. You can see how it works on the picture. For the first case, for the biggest noise and for the smallest noise. And the last experiment, we take the following function. But here we consider two types of noise. The first type of noise is a random noise, and the second type of noise, comes from the some quadrature formula. And as this quadrature formula, we take a Cléchau-Curtis quadrature, and it's look like that. Yes, and as a result of such approximation, you can find here, we recover second derivatives of the function. And as you can see, for the random noise, this is this table, and for the noise from Cléchau-Curtis quadrature formula, it is the same, completely the same. I think here's the picture also. Here's a picture. And here's some our recent publication concerning to this topic. So it is maybe not all publication, but some publication maybe. And also we have some perspectives. We would like to investigate another polynomial systems such as Jacobi polynomials, Hermite polynomials, and Laguerre polynomials for numerical differential problem. And also we would like to take a posterior rule for choosing discretization parameters, because a posterior rule doesn't depend on the smoothness of the function. But as you can see, now we have a priori rules for choosing of these discretization parameters. It depends on the smoothness of the function that we should know in advance. So thank you for your attention.
Thank you again. How extent we will present Miloš Tetor, and he will speak Miloš and Pavel. Pavel is from Green Polytechnic, and Miloš will speak about lattice quantum graphs. Please.
Thank you for the introduction. Thank you for the introduction. As you see, I at Jambul Yusupov because he contributed also to this topic. So my talk has a very vague name. So let me first tell you what do I mean by this name. If I try to, next slide, please. Okay, thank you. With production of very sophisticated nanostructures, also it goes well with some mathematical description, and the materials that people are now able to construct, able to tune, are usually called metamaterials, which are man-made materials, and their potential is very large, and the main reason is that they can produce highly non-trivial and exotic properties. Among others, for instance, if you have an interface of two such materials, you can get very strange refraction called negative, for instance. You can steer the beam, you can perfect lensing even before, even farther than usual technique allows. So lattices become to be customizable. It means at will you might be able to produce material that fulfill your demands. Concerning mathematical view on this technique, it means that you must know the band structure they are usually modeled as, if they are modeled as quantum graphs, they are modeled as periodic structures. And, oh, sorry. And what is important is to know the band diagram, the structure of bands. As time passes, many regular lattices have been studied, both planar and three-dimensional. And there is important also not the structure of graph, it means the geometry, but also you must pay attention to vertex coupling. And vertices in this sense act as scatterers that model resonant elements posed in the node of the lattice, and they are usually this is super wavelengths, which means that that usually are constructed such that influence scattering in the vicinity of this element of this node. So from the mathematical point, it is a rather complicated structure because the resonant elements are also modeled as open graphs, usually finite number of elements, but nevertheless you have the main structure, and in the nodes you have a substructure. So you can imagine that the mathematical this description is rather non-trivial. So an idea is whether it could be possible to stay on the main level. It means to have the quantum graphs, and instead of specify structure of the node, attach or assign some waves, some weights to the edges, and maybe it will model very superficially. Nevertheless, it could model some behavior that is able now to be produced. Well, this is the idea. Let's see whether it is feasible. Okay, so from our description, so we have Schrödinger operators supported by graphs, and this is something like Hamiltonian in quantum systems. This is something you have heard here several times, because we require self-consistency of this operator. So it implies that vertex coupling couldn't be any, but must fulfill some conditions. This actually is a restriction on it, on those couplings. The aim of this say study is to find band structure and perhaps conductive properties, and look whether they are influenced by those weights. So we studied basically two cases, very simple, namely linear chain, which is structure periodic in one dimension, and regular rectangular lattice that this is periodic in 2 dimensions. And we have chosen the simplest actually couplings, which is delta coupling, and if the coupling constant is 0, it's called Kirchhoff coupling. So this is what I mean by this periodic structure in 1 dimensions. I call it barbed wire. You have two finite parts attached in each node to the infinite line. The structure is periodic, so we can mark the elementary cell, unit cell, if you prefer, and now we proceed in a standard way. It means that due to the periodicity in the x direction, we can apply Bloch-Floquet method. Bloch is from physical community, Floquet from the mathematical community, and we can write the Hamiltonian as this integral, and the spectrum then is written here. This is union of spectra of this fiber operator as this theta parameter runs over the Brillouin zone. There should be, if I have here L1, there should be pi over L1. Yeah, so we know how to find spectra, and now let's form the wave functions. First of all, okay, here in these outer ends, I pose the Dirichlet boundary conditions, which means wave function in this points is 0. And I take it into account when writing down the answers for the wave functions. I see there is a mistake because there should be minus. I'm sorry. Now I pose this Bloch-Floquet conditions written down. So we have conditions on wave functions, but decoupling. Yeah. So coupling is written here, as which is actually four equations, and Bloch conditions are 2 equations. So together we have 6 equations for 6 unknowns. It means A1, B1, A2, AC, BC, A4. Okay, so I have system actually singular. So I must require that determinant of this system vanishes. This is explicit form of the matrix or of the determinant for alpha equals 0. Alpha non-zero, this is one minor complication, but for the sake of place, I leave it out. So vanishing of this determinant gives us spectral conditions. It means that if this equation is fulfilled, I find such a k that can k and theta runs over the Brillouin zone, and k is actually the root of this spectral conditions. Negative spectrum could be found by substituting I kappa for k, kappa positive. what we get. The lines in black shows limits in which cosine moves as theta runs over the Brillouin zone, and the curves in green actually depicts a graph of the right-hand side. So you see that it could be fulfilled. You can if you fix theta, you can find k that this is fulfilled only in those parts where the curve in green lies between these two limits of cosine. So this part is part of spectra. The same here, and so on. So in such a way, we get a system of intervals that gives us positions of band spectra. You don't see any so-called flat bands, and this is question. Theoretically, there shouldn't be flat bands, but there are some accidental bands. This is the same situation depicted as a 2D diagram. Here you show. Here you have theta running from minus pi to pi, because I have chosen L1 to L to unity, sorry. And here runs K, it means quasi-momentum. And again, these are solutions of spectral conditions, and you see that this is a situation when you have solution, and therefore this is a band. Yeah, but there are, for instance, two flat bands, not visible in this previous picture, and this is due to specific value of length of those finite parts. Yeah, this rational lengths can annihilate the spectral conditions. So you must be careful from this point of view. Yeah. Well, if alpha is non-zero, situation does not change much. Let's look first on the. By the way, the first formula is again spectral condition for alpha equals to 0 if you look for negative spectrum. So let's look first on the right-hand picture. The changing alpha, you get different curves. Nevertheless, you see that the character of the spectra is very similar. On the left, you have a situation for negative spectrum in the in this axis, you have kappa, which is positive, so kappa runs in this direction, and you see that, for instance, the curve in red does not crosses the black primes, and therefore we have no negative spectrum, contrary to these curves in green, which crosses the spectrum and crosses the strip, and we can have in this part we have negative spectrum, it is attached to 0. Now I come to the situation I mentioned in the introduction. Let's attach to every psi, every wave function, weight C1, C2, C4, and again repeat the situation. It means again I have here Kirchhoff condition. Now you see that the situation is rather similar. What happens are those coefficients in front of those terms, and if you do analysis of band structure, you see that there is practically no change in character of spectra. So playing with C's, we don't gain much. Well, what about in 2 dimensions? Let's study rectangular lattice. Again, we must write down the ansatz for wave function. We have the same delta coupling in the node, in the vertex, and again now we have 2 conditions from periodicity. So again we can solve the system, or more precisely we may find the condition where the system has solutions. This is written here. And if I have a square lattice, then I have simpler situation, and I add also the alpha, which is actually delta condition. So situation looks like again similarly as in 1D case, and is sufficiently simple. If you try to find the solution, you must now have a Brillouin zone as a rectangle, as a square actually, or rectangle if you have different sizes of the structure of the lattice. So here you see that we have flat bands. Here is flat band. Here is flat band, and some surfaces that show you the structure of bands. Well, and now what happens if we include the C's, the constants? Spectral condition is more complicated. Nevertheless, again, the structure is very similar as in the 1D case, in the periodic barbed wire. If we put them, I mean, constants to unity, then it comes back to the original situation. So there is no problem. And maybe interesting situation could arise if you have square lattice and C2 equal to C4. It means there is no left-right asymmetry. In that case, again, the condition is written explicitly. But if you produce bands, if you look like bands look like, again, it's a continuous change. But there is at least I don't see any way how to achieve a certain asymmetry. Because even from this condition, you see that this probably does not produce any asymmetry. And you maybe say it might be interesting to see probability currents. Well, probability currents could be write down explicitly. A1 is because it is the system of linear equations. So you have one free constant. Let's choose it A1, and then you have explicit formulae for currents. Yeah, again, from 1 to 3, you have the same expression. From 2 to 4, again you have the same expression. So my opinion is that this idea is oversimplified, and you might object that perhaps more involved numerical study could reveal something. For instance, to send a wave packet in one direction and look how it evolves. But probably this doesn't meet your original idea or our original idea. So maybe another study might help, but frankly, I'm not much optimistic. So probably I won't keep you long.
Questions?
Maybe Pavel can
If I may have a comment, can you go back to the dark wire?
I would like to.
Yeah.
Sorry.
Back.
I know. Yeah, it
Yeah.
works.
Right.
Not yet.
Water is back.
Refuses.
Still back.
Right. Tell me what to do.
Can you go back?
Please could you go back?
Yeah.
Okay.
Yeah.
Okay.
Now, Jambul introduced this transparent vortex condition and showed us an example where you have a branching graph. There's a wave packet which goes only through, does not return. Basically, that's the property which, in fact, works only for plane waves, because if you want to have his saying is that you need a wave packet which is localized at one of the edges, right? Which is that the support is at most a half-life. And now, if you take a spectral decomposition, we know from the Fourier analysis that if you have a function which has a support on the half line, then the Fourier image has the support on the whole real line. So in the spectrum of such a wave packet, there are always waves which are both there and there. Of course, if you take, it does not matter in your case, if you have a long edge and you put your wave packet far away, so then the component going back is negligible. But this example shows that if you have a finite, and you don't have a localization, strict localization, much smaller than the distances, then suddenly this transparency is lost. Because you see that the spectrum is perfectly, there is no asymmetry here. So that's, I think, the main lesson of this model.
Are there questions now? If not, we think. Then go directly to the next talk. Please. Next topic is something. The next presenter is Arturo Wilson. He will speak about spectral properties of Laplace operator interconnected unit squares.
Squares.
Pronounce it correct. Squares.
Yes.
Okay. Arturo Wilson is from Ilmenau Technical University. Please.
Yeah, thank you. So, yeah, I think we can go ahead and talk about the setup.
A microphone, please, better.
Better? Okay. Hi. So we'll go ahead and talk about the setup. So the setup is good. So I have a setup of infinitely connected squares horizontally. So you can imagine this bottom part to be the x-axis and the top part to be 1 unit up. And I'm taking the unit square, so it's just a unit length, and unit length uniform everywhere. And I want to consider Laplace, but minus Laplace on one square, but the next one is plus Laplace, and then minus Laplace. It just alternates. So on. And for a boundary condition, I want Dirichlet on the bottom and Dirichlet on the top. And we'll discuss what conditions we can put on the red boundaries. Okay, so we start with a familiar definition of a symmetric operator. So all it means is you can interchange the operator in the inner product and you get 0. So I think it's a familiar definition, so I won't spend too much time on this. And as an example, I have, we can take, let's say, smooth domain. I think this is the older one. Smooth domain in Rn, and the Laplace operator. And if we work out the inner product without any boundary condition on the boundary, we end up with, by the Green's identity, we end up with this equality. So for this operator to be symmetric, well, at least, so this Green's identity has to be 0. And why do I want to study this? Because I'm interested in exactly when a symmetric operator is self-adjoint. And for a necessary condition, the Green's identity that I just said above has to be 0. Well, it has to make sense, first of all. We have to take classes of functions here, f and g, that you can integrate like this. So namely, we want g to be g and f to be differentiable on the boundary. And then we can integrate, And the second condition is, of course, after making sense of it, I want this to be 0. I want this Green's identity to be 0 and some analytical
details to be mentioned or maybe not mentioned later. Okay, well, here's what we have a classical example, also Laplace, but the domain I chose carefully so that it's self-adjoint. Okay, and an abstraction of this, okay, so the plan of my talk. Yeah, I can skip this actually. So the abstraction of this concept is a boundary triple. Actually, I won't use a boundary triple. In fact, I'll use a quasi-boundary triple. We start with a densely defined symmetric operator A and Hilbert space H and G. So H plays a role of the domain of A, where the domain of A is contained in, and G plays the role of the boundary Hilbert space. I'll give an example to make this clear. Okay, and T is an operator, some linear operator whose operator closure is the adjoint of A, and the boundary maps. So gamma 0 and gamma 1, and these are exactly, so these maps generalize the Green's identity. So I just subtract TF inner product with G and F inner product with TG. I take the difference, and I want this difference to end up at this quantity. So this quantity, in the example, I'll make it clear how this is a generalization of Green's identity. But, okay, so I want this identity to hold, and for technical detail, I want this map to be dense in the target Hilbert space, so in the boundary space. Okay, and yeah. So in the case of for example, things like quantum graphs, what they have is what's called ordinary boundary triple, where this map is surjective. It's not just dense, but they have it surjective, which is also common in the case of one-dimensional case, but I have a PDE, so we typically don't get surjectivity. Okay, and then, so once all these are satisfied, we call this triple, a quasi-boundary triple for A star. Okay. And then as an example, okay, we can take the same example. So smooth domain Laplace, and I define these maps to be, the boundary maps to be gamma 0 to be the evaluation at the boundary, and gamma 1 to be the normal derivative. So here I just mean outward normal. In practice, it doesn't really matter. So then I take the difference, and here's just the Green's identity that I wrote down earlier. So just to recall, it's this one. It would work out to be this one. Okay. And then, yeah, so yeah, I forgot. So F is from H2. And then, okay, so the range of this, I call gamma total map of collective map of gamma 0 and gamma 1. The range of it is some Sobolev space, which is dense in L2. This is exactly how we don't get surjectivity in the case of PDE, higher dimensional domains. So yeah, okay, yeah. And then here, this is also some technical analytical detail that I didn't stress, but the A0, which is the T restricted to the kernel of this gamma 0, which is just a Dirichlet boundary condition. And then, yeah, so that was also this last condition that I didn't stress, but it's important. So, okay, so that's self-adjoint. So, okay. So in the previous slides, okay, these maps, okay, I just wrote it down as though it's an evaluation, but okay, it is an evaluation in practice, but mathematically, they have to be interpreted as trace maps. So okay, so what one has to know is that, okay, so I can evaluate it on some classes of functions. So namely, if it's continuous on the boundary, then I can evaluate it. The trace map is an appropriate lifting of this evaluation map to the space that we're interested in. So there are many, many articles on this, but I decided to cite this one. And here, the other thing is, okay, the domain doesn't have to be smooth. It can have Lifshitz boundary. So this is the most general boundary condition that such that a nice trace theorem can be proved, can exist. Okay. So here, yeah, I just wanted to say that, okay, evaluation at the boundary is justified via these trace theorems. Okay, so revisiting the infinite rectangle, or rather interconnected unit squares. So just to recall the setup, I have infinitely many unit squares joined horizontally. And on each square, I have either minus Laplacian or plus Laplacian. And yeah, so, okay, that's all. So yeah, mathematically, it's like this. Okay, so the operator is plus or minus Laplacian and infinite direct sum of this. And then the Hilbert space is also the infinite direct sum of each of those squares. And then I want to study this operator, how it acts. And here I chose the domain to be, so H2, who's on the interconnecting boundaries, I just want functions here to on this boundary here. For example, the functions here and here to agree on this boundary. And likewise, the functions here and here to agree on this boundary. Okay, so that's what I mean by this red condition. And the blue condition says it's the functions take value 0 on the top and the bottom. Okay. So it's almost like Dirichlet, but I have this what we call a continuity condition on the interconnecting boundaries. Okay. So here, just as a summary, it's we take the same operator in viewed as an operator in L2. And we take the domain. Okay, it's written differently, but it's the meaning is the same. It's continuous on the interconnecting boundaries. And I take this map, so evaluation at the gamma 0 to be the evaluation at those vertical boundaries, and gamma 1 to be the it's kind of like Kirchhoff condition. We just add derivative, normal derivative coming from this side and this side. So we just add them, and then so those are the boundary map. And once we take this, what's it called? L2 of the boundary of each square, then it's quasi-boundary triple. So I think here the range of this map is H3/2, and the range of this is H half. So it's dense in here. Okay. So one of the tools. So okay. Then so what? I want to study. One of the things I want to study here is the spectral properties of yeah, this operator, or rather, no, sorry. Yeah, so I want to study the spectral operator of this, and one way to go by this is, okay, I can take gamma field and Weyl function, and they connect the spectral information between, what's it? I forgot to write down T, but so basically I restrict the operator to the kernel of this and kernel of this. If I restrict the operator to the kernel of gamma 0, then it's basically Dirichlet boundary condition on each of the squares. So it's automatically self-adjoint, and this one, if I restrict the operator to gamma 1, that's a little bit more difficult to study, and that's basically what I want to study. And one tool is this gamma field and Weyl function. So they connect the spectral information in between those two operators. So the definition is here, but I want to go ahead and show the computation. So gamma function would look like this. So actually easier object to compute is the adjoint of gamma, which is so the big gamma 1 times the resolvent operator of the kernel of gamma 0. So then, yeah, I compute this via Green's function and then do some integration by parts. And I get this. So this is the gamma field, how it looks on each of those squares, where these A and B are these functions. So they're not exactly constants. They still depend on Y, but okay. And then they also, of course, depend on E. And these A and B in this constants come from the fundamental. So when we solve the fundamental solution for Green's function, there's what is it? Laplace minus lambda equals delta. So when we solve this equation, it comes out as an artifact. So they are expressed in terms of this lambda. So when we go back to here, the definition, so this lambda, so it would be expressed in terms of this lambda. So they're a little bit long to write down, so I just wrote down as A and B, and they don't play a big central role in this. Okay, then the gamma field. So what I computed above is the adjoint, and then now I have to do integration by parts. So then, yeah, I shift things around, so I get this expression. Okay, so yeah, so now then I can easily compute the Krein's resolvent formula in order to relate this operator A0 and A1, which are respectively the kernel of big gamma 0 and gamma 1. So in the classical example, you can think of it as estimating the spectral information about the Neumann operator versus the Dirac operator from the Dirac operator. Sorry, Dirichlet, not Dirac. So this is the yeah, classical way to think about this. Yeah, okay, as a summary, yeah. So then, yeah, so this A0 was the easier operator. Everything is decoupled on each square. And this is the coupled operator where I have some interconnecting condition on the boundaries. So I really want to learn about this. And then, well, I want to show that it's similar to a self-adjoint operator in a Hilbert space. So this, I hope I can report in the next meeting. Thank you.
Questions? I have a question.
Yeah.
Since you have these squares and then delta and minus delta in neighboring domains, yes? Do you need some compatibility conditions for the boundary conditions on this?
Yeah, so those are the boundary conditions on this vertical. Yeah, so I have it here. Yeah. Yeah.
Other questions? Then, thank you again. And now it's a very proper break and there's no change in the program. Sultan, some will give this talk tomorrow. Is he ready to give us immediately after coffee break? Yes? Okay. Yes. Immediately after coffee break. Fundamental of indirect control system with rigid feedback. Salvador is from the Institute of Mathematics and Mathematical Modeling in Almaty, Kazakhstan. Please.
Thanks for your introduction. My talk is Paul. And так. Не слышно? Слышно? Хорошо. Beginnings of in this problem of ordinary differential equations goes back to the 50s years of last century. The first work was published by Irugin, construction of the entire set of systems of differential equation by given integral curve. And further, this direction was developed by Garuin, Mohamedjanov, Mukharlian, and others, and to construction program motion system for solving dynamic inverse problems and analytical construction of system program motion and construction of system control of automatic system. And in the space we selected domain one. In this domain, we consider the problem of constructing for a guidance smooth program manifold, the follow system of differential equation. X, F and X is dimensional vectors, F some vector, and satisfies conditions of existence solution. That. And the program manifold defined by the equation 3. Equations. Вот так, да? Equation 3. Where omega is dimensional vector is less equal to n is continuous in the domain 1, including the manifold omega together with its derivatives. Oh. Да. This program performed exactly only it satisfies the condition of initial values. Omega equal 0 of the system state vector. However, this condition not always satisfies due to the presence of other perturbance forces. So when constructing program motion control system, it is necessary to take into account the stability of the program manifold with respect to some function. Composing a necessary and sufficient condition that the program manifold is integral for the system, we obtain it omega equal to expression 4. Where f is some Erogen function and satisfies condition, this condition in on program manifold equal 0. H is Jacobian matrix and its rank is equal to S at all points of omega t. Together with equation 1, consider the indirect control system with mixed feedback of the following structure. This B constant matrix, Q is constant matrix of rigid feedback, and phi sigma differentiable with respect to sigma and satisfies following conditions 6. Here K is symmetric matrix. For the manifold omega to be integral, also for the system 5 and 6 on the manifold omega equal to 0 is necessary condition Xi equal 0. This condition is satisfied only if only when Q not 0. Taking into account expression for choosing Erogen function linear with respect to vector function omega, differentiate the program manifold 3 in time by vector of the system 5, we obtain the following system. It is Popov type system with respect to vector function omega. Further, we investigate system 7. Here, non-linearity phi sigma satisfied condition 6 not 2. And means A is Hurwitz matrix, H and B express this relation. F equal to minus A omega. Definition, program manifold of indirect control system with rigid feedback is called absolutely stable if it is globally stable on solution of system 5 for any omega and phi sigma satisfying condition 6. And statement of the problem finds the absolute stability condition for the program manifold of the indirect control system with respect to the vector function omega and the condition 6. For the system 7, we construct Lyapunov function of the form quadratic form plus integral from non-linearity in the form of 9. Where L and Q positive matrix, beta is diagonal positive matrix. Так. And the derivative is equal to 10, where C and C1, C2 expressed it by in terms of our system. In order for it to be minus omega derivative, V derivative will be positive, it is enough to fulfill Sylvester's condition. This condition is 11. And our conclusion. Let the Irugin function was chosen in the form 8. The non-linearity satisfies condition 6, and definitely positive matrix be guiding. Then for absolute stoichiousity of the absolute stability of the program manifold of Popov type systems with respect for vector function omega, it is sufficient to satisfy Sylvester's condition even. So further, we move to the new system in coordinate omega and sigma in the form of 12, where G is expressed this relation. For the system, we construct Lyapunov function in the following form. Again, in the quadratic form plus integral from non-linearity, the matrix L M N satisfies next conditions or end. Beta is also positive matrix. And the same way, we in the different what is requested the performing of equal 16 and 17. Then for it minus B derivative was positive, it is enough to fulfill Sylvester's inequality of the following form. So is valid the next theorem. Let the Irukhin function was chosen in the form linear to the with respect to vector function omega, non-linearity satisfied conditions 6 and inequality 14 are true. Then for absolute stability of the program manifold of Popov type systems with respect to vector function omega, it is sufficient to satisfy Sylvester condition. And comment, so the equality is 16 and 17 can be used in the construction of the Popov type system to find matrices P and Q. So, and for the list references and our last our list of our paper in the following form. It is last our publication, and thank you for attention.
Questions? Questions, remarks?
It is clear.
Thank you again. We start with this one, or there is some changes in program. There is written 10 search. Today's session is over. See you tomorrow.